Our next section is law of large numbers. This law of large numbers is a very important concept in statistics. In simple words, law of large numbers offers a mathematical relation for lot of common phenomena occurring in our real life. In sampling distribution, we found that sample mean is a variable while population mean is a constant. We know that sample mean is an example of statistic and population mean is an example of parameter. Generally, statistics are variables while parameters are constant. Also note that when sample size increases, the difference between sample mean and population mean becomes smaller and smaller. This is because when sample size increases, more and more units of the population will be included in the sample. So for large sample size, the difference between sample mean and population mean will be negligible. For example, consider a case of a random experiment of throwing a die and observing the number on the face of the die. We know that this expectation of number on the face of the die or average of the face of the number of the die is 3.5. But when you observe the number on the 3 or 4 throws of the die, you can see that sometimes this mean will be far away from 3.5. But when we increase the number of throws and observe the number on the face each time, average of those numbers will be very much close to this population mean 3.5. This property of large numbers is considered in this section. We have to discuss mainly three principles of large numbers. But before we come to this principle of three laws of large numbers, we have another result to discuss known as Chebyshev's inequality. This Chebyshev's inequality offers an upper or lower bound for probability of a random variable from its mean. Actually, this idea of Chebyshev's inequality was originated from the measure of dispersion. We know that some variance or standard deviation is a very better measure of dispersion. When variance becomes smaller and smaller, these observations will be very much close to the population mean or representative. That is, the observations are not scattered from this representative of the observation, that is arithmetic mean. Based upon this property, Chebyshev's inequality was introduced. The most important features of this Chebyshev's inequality is its generality in nature. We don't need more conditions on the variable or its distribution of the variable. It is only that requires only very minimal conditions. They are regarding mean and variance. The mean and variance of the data should be finite. These are the only two conditions imposed on this Chebyshev's inequality. So Chebyshev's inequality in simple words states that probability that an observation will be more than k times standard deviation from the mean is at most 1 by k square. We have now the statement of this inequality. The statement gives that if x is a random variable for which mean is mu and variance sigma square, then for any number t where t is positive, probability of modulus x minus mu greater than or equal to t sigma is less than or equal to 1 by t square, or probability of modulus x minus mu less than or equal to t sigma is greater than or equal to 1 minus 1 by t square. This is about this Chebyshev's inequality. Here we assume x is a random variable with finite mean, that is mu, and variance sigma square. And there is no mention about the distribution of the random variable. We are given only the mean and variance. Now we have another constant t, that is a positive number t. Now the inequality shows that modulus x minus mu, that is the absolute difference between the variable value and the population mean. The absolute difference between those two things greater than or equal to t times the standard deviation is less than or equal to 1 by t square. That is the first part of this inequality. The second part is simply the complement of the other. That is, this inequality reversed, greater than or equal to becomes now less than or equal to So it is probability of modulus x minus mu less than or equal to t sigma greater than or equal to 1 minus 1 by t square. In short, this Chebyshev inequality offers a probability of this observation and the mean absolute difference less than or greater than t times the standard deviation is at most 1 by k square or at least 1 minus 1 by k square. Now we come to the proof of this result. The proof begins with the definition of this variance, and before that we consider the proof for a continuous variable only. We can make a similar proof for discrete variable also. So without loss of generality, we assume that x is a continuous random variable and the variance of this variable sigma square is defined as expectation of x minus e of x whole square. That is, in the present case, e of x equal to mu, that is e of x minus mu whole square. Now, we don't have any density function of the variable. So we are making use of actually the uh, theoretical proof of this result, not in particular this density function, etc. So by definition of this expectation, this is integral minus infinity to infinity x minus mu whole square f of x dx, where f of x is the PDF of x. We don't know its equation. We are generalizing the PDF. It is given by f of x. Now, this integral has been split into three intervals. The three intervals are, one is minus infinity to mu minus t sigma, second is mu minus t sigma to mu plus t sigma, and the third is mu plus t sigma to infinity. I shall take the pencil to represent these different segments of the entire interval. Yes, so suppose this is the total range of variation, that is from this point minus infinity and somewhere in middle 0 we have, and also we have this plus infinity. Suppose the mu is located here. Okay, so not mu is somewhere, this is the location of mu minus t sigma and this is the location of mu plus t sigma. So the entire integral from minus infinity to plus infinity has been split as minus infinity to mu minus t sigma, the first part, and second part is mu plus t sigma to mu minus t sigma to mu plus t sigma, and the third is from mu plus t sigma to infinity. So these are the three. So in total it is again minus infinity to plus infinity x minus mu whole square f of x dx. Now we consider the uh, integral in given the middle. Okay, that is x minus mu whole square f of x dx. Know that x minus mu whole square is always a positive value because of the square. Now, f of x is the PDF. It is by definition also positive. Therefore, x minus mu whole square f of x is a positive quantity. Therefore, its integral from minus infinity to its integral from mu minus t sigma to mu plus t sigma will be positive. So, if you ignore this term in the next step, this inequality will be imbalanced. That is, actually this is now sigma square equal to, but if you ignore this term, this inequality will be, now equality will be changed as sigma square greater than or equal to minus infinity to mu minus t sigma x minus mu whole square f of x dx plus mu plus t sigma to infinity x minus mu whole square f of x dx, because it was balanced because of the three terms and the middle term not only is positive. So if you ignore a positive quantity from this balanced equation, that will be imbalanced and the equation will be the right side greater and left side smaller. That is why sigma square greater than or equal to minus infinity to mu minus d sigma, etc. Now we consider the integrands one by one. The first one is uh, in the first integral, the range of variation is from minus infinity to mu minus t sigma. That is, the variable x has variation from minus infinity to mu minus t sigma. That is, x is less than mu minus t sigma. So x minus mu is less than or equal to minus t sigma, and therefore x minus mu whole square is greater than or equal to sigma square. Here we have to write less than or equal to also. So in short, x minus mu whole square will be greater than or equal to sigma square. Because of this negative value, this inequality will be reversed. You know that the t is by definition positive, sigma also by definition positive because it is a standard deviation. So this quantity t sigma will be positive. Okay, so this T sigma positive, so a minus sign, so this is totally negative. So this left side is less than or equal to a negative quantity. So that's definitely this will be also negative. So it is like the minus 2 less than or equal to minus 1. Okay, so when you square both sides, what happens? The inequality will be reverted. That is x minus mu whole square will be greater than or equal to this sigma square. So when we come to the second now, third integral actually, or in here the second, it is integral minus integral mu plus d sigma to infinity x minus mu whole square f of x dx. In this case, x is always greater than or equal to mu plus d sigma. So x minus mu is greater than or equal to t sigma. So x minus mu whole square is greater than or equal to t square sigma square. Now, in short, in both first and second integral, x minus mu whole square is greater than or equal to sigma square. So we shift these two x minus mu whole square in the main answer, that is by t square sigma square, that is sigma square greater than or equal to minus infinity to mu minus d sigma t square sigma square f of x dx plus mu plus d sigma to t square sigma square f of x dx. That is by replacing this x minus mu whole square and this x minus mu whole square, and we are replacing by its least value, that is t square sigma square. That's why the inequality unchanged, that is t square sigma square is a common factor, so it is taken outside. Now integral minus infinity to mu minus d sigma f of x dx, mu plus d sigma to f of x dx. Now note that this side, that is the first integral, represents a probability. That is, we are integrating a density function over some interval. So when you integrate a density function over some interval, the resulting value will be the probability of that variable lies within those lower and upper limits. Therefore, this integral gives probability of uh, x between mu minus t sigma and x is less than or equal to mu minus t sigma, and this is x greater than or equal to mu plus t sigma. That is, this is an open interval. Here the lower limit minus infinity, and here the upper interval lower limit minus infinity, and here the upper limit plus infinity. So that is, if you write x this as x minus mu less than or equal to minus t sigma, then x minus mu greater than or equal to t sigma. Now these two can be closed in a single interval. That is, this is like, if this is the place of x minus mu, this, I'm sorry, not x minus mu, if this is less than or equal to minus t sigma, if this is less than or equal to minus t sigma, and the other is, this is at 0, these two are equidistant from 0, and this is t sigma. The first interval shows that x minus mu less than or equal to minus t sigma. That is, the first interval shows that desired. Okay, that is minus infinity to minus t sigma. The other interval shows that t sigma to infinity. That is x minus mu greater than or equal to t sigma. We can close these two intervals in a single interval, making use of modulus sign. Or the middle part, that is minus t sigma to plus t sigma, will represent modulus uh, x minus mu less than or equal to t sigma. That is, x minus mu lies between minus t sigma to plus t sigma. That is when the inequality less than or equal to. Or if you open this x minus mu less than modulus x minus mu less than or equal to t sigma, that will be minus t sigma less than or equal to x minus mu less than or equal to t sigma, and which is given by this section, that is these two, that is minus t sigma to plus t sigma. Now you have a complement of that side, that is minus t sigma or lesser, t sigma or greater, and that is those two things are given in this interval, x minus mu less than or equal to minus t sigma, then x minus mu greater than or equal to plus t sigma. So their probabilities can be combined with the help of a modulus sign, that is t square sigma square probability of modulus x minus mu greater than or equal to t sigma. That is 1 by t square greater than or equal to probability of modulus x minus mu greater than or equal to t sigma. Or write in the reverse order, that is probability of modulus x minus mu greater than or equal to t sigma is less than or equal to 1 by t square. This is that one part of Chebyshev's inequality. Naturally, the other part is the complement of this, which can be written as probability of modulus x minus mu less than or equal to t sigma will be greater than or equal to 1 minus 1 by t square. Now, making use of this Chebyshev inequality, we have the first law of large numbers known as Bernoulli's law of large numbers. As a beginner of probability, we had seen that there are three approaches to probability. The first approach, classical approach, in that approach we found probability as a ratio of two numbers, the two numbers representing the number of elements in the sample space and also the number of elements in the uh, event. And next approach we have frequency approach to probability, or the definition based upon statistical regularity. In this case, we found probability as a limiting value of f by n. And what is f by n? F by n is the frequency ratio. That means if A is an event defined over sample space, and if you repeat the experiment n times, and f is the number of times the event A appears, the frequency ratio of A is f by n. We found that in this approach, when the number of trials becomes larger and larger, this f by n becomes closer and closer to some value, and this n tends to infinity, f by n, this value to which this frequency ratio becomes closer and closer, is known as the probability of the event. That is the frequency approach to probability, or this definition of probability based upon statistical regularity. Now, this Bernoulli of large numbers is actually an interpretation of this uh, frequency approach to probability in a different way. That is, we have a random variable xi. Xi is 1 if success and 0 if failure. Suppose p is the probability of success, then probability of failure will be 1 minus p, that is q. That is, xi is equal to 1 if success and xi equal to 0 failure, and p of xi equal to 1 p and p of xi equal to 0 q, where q is 1 minus p. We have found that e of x is equal to np and v of x is equal to npq. Now we consider x by n. X by n is actually the frequency ratio, that is, x is the number of successes, n is the number of trials. Therefore, x by n is the frequency ratio. In Bernoulli's law of large numbers shows that probability of absolute difference between x by n and p less than epsilon tends to 1 as n tends to infinity. And what is the meaning of this relation? That is, probability of some event becomes 1, means probability becomes sure. For which event the probability becomes sure? The difference between this x by n and p less than epsilon. Epsilon represents a small value. Therefore, the difference becomes x by n and p becomes smaller and smaller when n tends to infinity, or the event of the difference between frequency ratio and p less than epsilon becomes sure. And it is actually this frequency approach to probability, that is, limit n tends to infinity, f by n is p of a. Here p of a is p, this limit n tends to infinity, f by n is stated using this probability of this x by n minus p less than epsilon tends to 1 as n tends to infinity. Thus, this Bernoulli's law of large numbers is another interpretation of this frequency approach to probability. Now we come to the proof of this Bernoulli's law of large numbers. We have e of x by n equal to 1 by n e of x, that is np by n, that is p, because x is the number of successes in n trials. So definitely x follows b and p, binomial distribution with the number of trials n and probability of success p. So its mean is np, its variance is npq. So e of x by n is 1 by n in e of x, that is np by np, and variance of x by n will be npq by n square, so pq by n. Next, we are going to apply Chebyshev's inequality on this variable x by n. So as we found in Chebyshev's inequality, we need only two things to apply Chebyshev's inequality. One is the mean of the variable considered, and second is the standard deviation of the variable considered. Here mean is p and the standard deviation is root pq by n. So the variable on which we consider Chebyshev's inequality is x by n. So it is like probability of modulus. The Chebyshev's inequality says that probability of modulus x minus mu less than or equal to T sigma is greater than or equal to 1 minus 1 by T square. That is the result of Chebyshev inequality. Here x is x by n, mu is pu, p, t is t itself, and sigma is root of pq by n. So we substitute all these things. So we have probability of modulus x by n minus p less than or equal to t root of pq by n greater than or equal to 1 minus 1 by t square. Now we choose this thing as the epsilon. This thing as epsilon. So we get probability of modulus x by n minus p less than or equal to epsilon is greater than or equal to 1 minus pq by n epsilon square. That is, if this is that epsilon, this 1 by t square will be pq by n epsilon square. That is by solving this equation. T is epsilon and n by root pq. So 1 by t square is pq by n epsilon square. Now we know that the maximum value of pq is 1 by 4. So if we write PQ with 1 by 4, we get, because P 1 by 2, Q will be 1 by 2, P 1 by 3, Q will be 2 by 3. So product of PQ will be less than 1 by 4. So the highest value for PQ possible is 1 by 4. So P of modulus x by n minus P less than or equal to epsilon is greater than or equal to 1 minus 1 by 4 and epsilon square. So what happens to this right side when n tends to infinity? When n tends to infinity, this side will disappear. That is, when n tends to infinity, probability of modulus x by n minus p less than or equal to epsilon tends to 1 as n tends to infinity. And that is the way we say this is actually a mathematical interpretation of this frequency approach to probability. That is, limit n tends to infinity, f by n is equal to p of a, or the difference between this frequency ratio and the probability becomes smaller and smaller, or becomes less than or equal to epsilon. That is the Bernoulli's law for large numbers. Thank you.